Hi, everyone. It's Zach here from In Your Element Tutoring, and today we are going to take a look at the 2019 AP Chemistry free response questions. And I'm going over this because I had a request from a lot of my students that I tutor to actually go over some of the FRQs since now with COVID and everything, the exams are, the majority of them are online. And because they're online, a lot of them happen to be free response based. So I thought it'd be a good idea to tackle some of these questions. So let's get started right away. And we're going to be going over the first long free response question for the 2019 questions. And normally this would take it should take you about 20 minutes to complete. However, we may be a little over, a little under, depending on when we finish. I'm going to try to go through it as quickly as I can. But at the same time, I really want to explain the chemistry behind each question to help you guys sort of get thinking about these types of questions and how you're supposed to answer them when you are going to face them probably coming this May. So yeah, without further ado, let's get started. So we got your periodic table of elements that they give you, your double-sided equation sheet. And here we go. Okay, question number 1. So the compound urea, H2NCO-NH2, is widely used in chemical fertilizers. The complete Lewis electron dot diagram for the urea molecule is shown below. So part A, identify the hybridization of the valence orbitals of the carbon atom in the urea molecule. Okay, so let me turn my camera off just so I can draw. All right, so the way I like to sort of do these problems, the way I remembered it, is to count the number of atoms surrounding the central atom that you're looking at, not the number of bonds, because if you see here, we have, let's first circle the atoms. Oh, whoops, I have to be on annotate. So we got 3 atoms, 2 nitrogens on each side, and then an oxygen at the top. And along with counting the number of atoms, you're going to want to count the lone pairs on the central atom. And as we could see, carbon's got a full octet. It has no lone pairs. And so the reason why I said don't count the bonds is because if you count the bonds, you have a single bond, which is a sigma bond, another single bond, and then you have a pi bond. And some people get confused and say, well, a pi bond is a double bond, so that's technically 2 bonds. So it's 4, and the hybridization should be sp3. Well, that's not the case because you actually only have 1 sigma bond in that pi bond. And so what we're doing is we're counting electron densities, the regions where the electrons are surrounding the central atom. And so we have 3 electron densities, not 4. And so each electron density is going to correspond to 1 letter and then eventually an exponent when you get to the p's. So 1 electron density is s, and then 2 is sp, and we have 3, so it's going to be sp2. And so that is going to be our hybridization. sp2. Right, simple enough. But it's important to look at the chemistry behind each question, just so you know how to easily do the identify questions without really having to think about them. Okay, so part B. Urea has a high solubility in water due in part to its ability to form hydrogen bonds. A urea molecule and 4 water molecules are represented in the box below. Draw 1 dashed line to indicate a possible location of a hydrogen bond between a water molecule and the urea molecule. Okay, so this is also pretty simple. If you remember, a hydrogen bond is a bond between a hydrogen, obviously, and another strongly electronegative atom. And those atoms are going to be oxygen, nitrogen, and fluorine. And obviously, we don't have a fluorine in here. And we do have nitrogens, but if you look closely, these nitrogens have a full octet, so they're not able to participate in hydrogen bonding. However, oxygen is available in multiple places, and you could sort of choose which one you want to do. And we have hydrogens available too. So all you're going to do is draw the dashed lines between 1, 2, 3, right there, just like that. And that will do. And like I said, any hydrogen and oxygen atom could bond in this picture, except ones within the same molecule, obviously. But okay, once again, pretty easy. Nice and easy point. Okay, so now we got our first calculation. So the dissolution of urea is represented by the equation above. A student determines that 5.39 grams of H2 NCONH2, molar mass 60.06 grams per mole, can dissolve in water to make 5 mLs of a saturated solution at 20 degrees Celsius. Part C, calculate the concentration of urea in moles per liter in the saturated solution at 20 degrees Celsius. Okay, so this is also a fairly simple calculation. You just sort of have to remember what the definition of molarity is, and that is moles of solute per liters of solution. So let's go into the whiteboard for this one. And I encourage you, by the way, if you haven't already, to sort of, as we go along, to pause the video and try these problems by yourself. And then once you're done, compare your answer to the answer I get, and see if there's any discrepancies, and go back and sort of check your work. But okay, part C. So we had 5.39 grams of urea, right? Apologize for my handwriting too. It's not the best. And we dissolve that in 5 mLs of a saturated solution, but it's moles per liter for molarity. So we got to convert that. So just do simple times 10 to the negative 3 conversion factor, and you will get 0.00500 liters of solution. And we're going to multiply that, or actually we're going to divide it by the molar mass of urea. So we have 1 mole urea, and for every mole there is 60.06 grams of urea. Nice and easy. They give it to you right in the problem. And okay, so if you get your calculator and do this calculation out, you will get, accounting for sig figs, you are going to get 17.9 molar urea. And once again, that's because you have 3 sig figs is the least number of sig figs in your calculation. So that's what you're going to use in your final answer. Okay, nice. All right. So once again, not too bad. Okay, so part D. So the student also determines that the concentration of urea in a saturated solution at 25 degrees Celsius is 19.8 molar. Based on this information, is the dissolution of urea endothermic or exothermic? So justify your answer in terms of Le Chatelier's principle. Le Chatelier's principle. The pronunciation is not that important, obviously, but the principle is extremely important for the exam. In fact, they always test this, and this is an example of it right here on the FRQs. And so really, the way you have to think about this, if you remember in Le Chatelier's principle, if you have a reaction that is endothermic, it's going to be favorable if you increase the temperature, right? And we have dissolution. So dissolution is obviously going to be a spontaneous reaction because you're breaking up molecules in a solution, and they're coming in contact with solvent molecules. And so there's more disorder, right? So that's obviously going to be spontaneous. And if you heat it further, for an endothermic spontaneous reaction, that's going to lead to the formation or the favoring of the products. And so the reason why this is going to be an endothermic reaction based on that principle is because of the fact that the increased solubility at that high temperature that you're going to be heating it at is basically alluding to the fact that the system is being stressed, and that stress is going to be counteracted by the further dissolution of the urea. And so I know it sounds confusing, but the best way to remember this is a dissolution. In order to dissolve anything, you need to apply heat, right, or stirring, or something to get the molecules to dissolve. And by doing that, by putting that energy in, that's making it endothermic, as opposed to exothermic, which would be the energy being given off. But yes, so that is D. Once again, a little trickier. These why questions are often the ones I find that students struggle with the most, really explaining sort of what's going on. People always worry about calculations. Oh, the calculations are horrendous and scary. But, a conceptual question could be just as difficult. But okay, so now let's get into some lab techniques. Part E, the equipment shown above is provided so that the student can determine the value of the molar heat of solution for urea. Knowing that the specific heat of the solution is 4.18 joules per grams degrees Celsius, list the specific measurements that are required to be made during the experiment. Okay, so this is also easy. It's sort of an identify question. However, you got to remember this is a calorimetry experiment, basically. And so if you remember calorimetry, you got your equation. Q, the heat, is equal to M, C, the specific heat, times delta T, the change in temperature of the system, right? And so based on that, you're basically going to need both masses, right, of the water and the urea, because one's going to gain the heat, one's going to, obviously lose heat to make sure that there is, the laws of thermodynamics are obeyed. And then, of course, you have the initial and final temperature of the water. So those four things are going to be what you need to measure for this experiment. So easy enough. You just got to remember your calorimetry. Okay, and now we have part F. Almost there, guys. The entropy change for the dissolution of urea, delta S of solution, is 70.1 joules per mole Kelvin at 25 degrees Celsius. Using the information in the table above, calculate the absolute molar entropy S of aqueous urea. So this, once again, also a fairly easy calculation. However, it's, some people could get this confused. We have to first look at the reaction to sort of do this calculation. So if you go back up here, you don't even really need this if you know what, dissolution is, and making something or dissolving something, in a solvent. Delta S is, as we know, equal to the S of the products minus the S of the reactants. And so obviously in a dissolution reaction, we're going to have the aqueous urea as the products, and you're going to be subtracting the S of the reactants, which is the solid urea that you're putting in. And we are given here the change, right? And we are also given the S of the reactants. So we're solving essentially for the S of the products, or the aqueous urea. So let's go to the whiteboard and set this one up. Okay, so this is part F if I'm correct. So you have your delta S, right? And we are given that to be 70.1 joules per mole Kelvin. And that's equal to, we'll just call this SP right here. So the S of products minus the S of reactants. And we're also given that. That's 104, whoops, 104.6 joules per mole Kelvin. Okay, so this is a simple algebra problem. You're just going to add the 104.6 joules per mole Kelvin to both sides to get the S of products. And that is going to be equal to, just do it on my calculator here. Okay, and of course, using sig fig rules, now we're doing addition and subtraction. So you're going to base it off of the least number of decimal places that there is, and that's to 1. So that is going to be 107. Oops, let's do this. $174.7 joules per mole Kelvin. Bam. And that is the answer to that question. All right, let's go back. 2 more problems. So using particle level reasoning, explain why delta S of the solution is positive for the dissolution of urea and water. Okay, so this one is definitely, once again, a higher level thinking question. And so normally, the simple way of thinking of it is that, actually for these last 2, I can just explain. So I guess I put my camera on. So yeah, so for these last 2, they're definitely difficult, but let's take it one step at a time. So for G, normally you would say that when you dissolve anything in water, or actually a positive delta S value is corresponding to an increase in disorder, right? Any increase in disorder corresponds to a positive delta S value. And so obviously we have a positive delta S value because you're dissolving something and you're breaking those solute molecules up in the solvent. And by doing that, you're creating more disorder because there's more molecules floating around, right? And more interactions between solvent molecules and solute molecules. But I'm not totally sure if that would get you the point on the exam or not, since that's a little simple. If you want to go deeper and really ensure that you get that point, the reasoning behind it is because you're increasing the number of possible molecular arrangements between the solute molecules and the solvent molecules. And as a result, you're going to increase the number of collisions and reactions going on between those molecules. And that is why there is going to be a positive delta S value, because of the fact that you have more molecular arrangements and positions of the particles in the solution. So a little tricky, but it requires you to think of entropy on a deeper level, other than just the fact that positive entropy is more disorder. But okay, so let's go to we're right here. H, the student claims the delta S for the process contributes to the thermodynamic favorability of the dissolution of urea at 25 degrees Celsius. Use the thermodynamic information above to support the student's claim. Okay, so this is also, you could base your reasoning. This is a mathematical reasoning, actually. Let me turn off my camera. So you got our famous Gibbs free energy equation. Delta G is equal to delta H minus T delta S. And okay, so obviously we know delta H is going to be positive, right? Because this is endothermic. We're dissolving something, so you have to put heat in. However, the reason why the reaction is going to be favorable thermodynamically is because of the fact that we also have a very high value for delta S, which is 70.1 joules per mole Kelvin. And that's a positive value. So you're subtracting a very high value from another positive value, but a value that's not as high. And so that is ultimately going to give you a negative value for delta G. And we know that if delta G is negative, that means that the reaction is spontaneous. So really, this one is just a mathematical reasoning question. You could even include this equation in there, but you have to explain that you're subtracting a large positive number from another smaller positive number, which will give you that negative. And that corresponds to a spontaneous reaction. Okay. So I hope this video was helpful. I hope you guys are doing well in AP Chemistry. As always, I am available if you want to comment on this video. You can find my contact information on our YouTube channel, and just reach out and I'd be happy to help. Like I said, I hope this video was helpful. Keep up the good work, studying hard, really practice these FRQ questions, because expect that these are going to be the questions they have on the AP exam come May. But yeah, other than that, thank you guys so much for watching. Peace out and stay safe.